Hi everyone, welcome to 4.3's lesson. This is on the strength of acids. We're going to start off example 1 by, with the following substances, writing the values of their pKa's. And remember, pKa is just the negative log of Ka. And then we're going to arrange them from weakest to strongest. So we're given the Ka's, 4 Ka's up there. We do need to add a couple more. The Ka of H2O equals 1.0 times 10 to the negative 14. The Ka of HCl, which we're going to need here, of hydrochloric acid, is just huge. It's about infinite. So it's huge because it is a strong acid. So it's like infinity. In reality, it's about 10 to the 7th, but it's infinity, really, because it breaks up 100%. So we're going to use 10 to the negative 7th for our calculations, because of course you can't plug in infinity. We also have NH4 here. So for NH4, that is going to be the conjugate acid of the ammonia base, so the ammonium conjugate acid of the ammonia base. So we can go ahead and just find that here. So our Ka of ammonium, NH4, oops, that's 4, plus equals Kw, or Ka of water, so 1.0 times 10 to the negative 14, over the Kb, which is right here, so 1.8 times 10 to the negative 5. And that, of course, comes from Kw equals Ka times Kb. So just as a quick reminder of where that came from exactly. And so that Ka, when you plug that in, is 5.6 times 10 to the negative 10. So our Ka of NH4 plus equals 5.6 times 10 to the negative 10. Alright, so on the bottom, we're going to go ahead and take the pKa's. Now, your pKa's are just the negative log of the Ka's. So, let's go ahead and write pKa here, and we'll do increasing strength here. Because we're going to rank these. So please take a second and find the pKa's for all of these Ka's. And then we're going to need to go ahead and rank them. So remember, when you plug it in, it's negative log of whatever. So for example, when you plug in the negative log of 1.0 times 10 to the negative 14th, the pKa should be 14. So pause this and go ahead and find those pKa's. Okay, so just showing you what I got to make sure it matches you. The Ka of NH4 plus, ammonium, is 9.3. HOCl up here, my pKa was 7.5. HNO2, which is right here, that's the pKa is 3.4. HF, my pKa was 3.1. And we don't have to do an H3 plus, a Ka here. This is about negative 7. So I plugged in this, of course, because you cannot plug in infinity. So pKa in pink. Okay, so those are all my pKa's. Now, the acids with a smaller Ka or larger pKa are weaker. So acids with the smaller Ka or larger pKa, because they're inversely related, are weaker. Strong acids, all strong acids, have a pKa that is less than 0. Now, why do we even do pKa's? A lot of textbooks and a lot of sources will show you pKa's instead of Ka's, so it's useful to know the relationship with both. So that's why we're doing pKa's and we're not just comparing Ka's. So let's find the largest pKa, because the largest pKa is going to be the weakest. So the largest I have here is 14, and that is water. And so H2O. And so that is the weakest. Next up, I have 9.3, and that's ammonium. So go ahead and pause the video right now, and you rank the rest of these and then come back and check. Okay, you have 7.5 pKa for HOCl, followed by 3.4 HNO2, followed by 3.1 for hydrofluoric acid, and then way, way, way smaller is your HCl. So that's the strongest acid. So the strongest ones are on this side, weakest ones are on this side. You can see the relationship with pKa and the strength of the acid. Okay, so here, arrange the following from weakest to strongest base. So for this one, you are going to need to find the KBs. So I want you to go ahead and pause the video and find the KBs for all of these from the KAs here. And if you don't remember exactly how to do that, use this formula. KW equals Ka times Kb. Your Kw is 1.0 times 10 to the negative 14. So go ahead and find the KBs for all of these, and then come back. Okay, so you can see I've written all of my KBs here, so go ahead and you can pause it and check to make sure that yours are correct. So the Ks, remember, with the smaller Ka or the smaller Kb, those ones are going to be the weakest. So let's do Kb here. This more clear. Kb. And then we're going to write these in order of increasing strength. Now you could also do pKb, but I just wanted to show you a couple of different ways to rank these. So of course the smallest one is going to be about 0, and that's chloride, and that makes sense because that is the conjugate of the strongest acid, so it's going to be the weakest base. So about 0 is going to be chloride. And then next up we have water, so H2O at 1.0 times 10 to the negative 14. Next up we have fluoride, right over here, 1.4 times 10 to the negative 11. Next smallest, NO2 at 2.5 times 10 to the negative 11, and that's right here. Next smallest, 2.9 times 10 to the negative 7, which corresponds with OCl minus. And then lastly, the NH3 is the strongest, the ammonia, 1.8 times 10 to the negative 5, and your ammonia, NH3. So just as a reminder, when we found these KBs, to find the KB, use KW equals Ka times Kb. Just to remind yourself when you're studying later. Okay, so the conjugate base of a strong acid is neutral. It's a neutral salt. Conjugate base of a strong acid is neutral. So that's why it's the weakest here, because it's actually neutral. And the conjugate base of a weak acid is a weak base. So the conjugate base of a weak acid is a weak base. The stronger the weak acid, the weaker its conjugate base. So let's write that association here. So the conjugate base of a weak acid is a weak base. That makes sense. The stronger the weak base, the weak acid, the weaker its conjugate base. So the stronger the weak acid is, the weaker its conjugate base is. So that's why you'll notice here these are pretty much flipped. Okay, example 2. Determine whether each of the following salts is acidic, basic, or neutral in aqueous solution. So aqueous means in H2O. So water Now we can write water as H2O, or we can write water as HOH. So I'm going to show you an interesting little trick to figure out whether the resulting solutions when you mix these with water are acidic or basic. So it requires that you know that this is H2O, so HOH, and we're going to write it right below the salt. So the first one is calcium chloride. So when calcium chloride and water react, we have calcium chloride and HOH. Now, what we're going to form here is, this is basically a double replacement reaction. So you have calcium plus ions and chloride minus ions. Hydrogen plus, hydroxide minus. So the pluses are going to switch places. And you end up making calcium hydroxide, so plus minus, and HCl. So let's write what we make. So we made calcium hydroxide, so CaOH2. And these are going to be balanced here, so you have to balance it here in your formula. And that, of course, we know is a strong base. And we also make HCl. HCl, again, we know is a strong acid. A strong base and a strong acid mixed together, and those form a neutral solution. So these will neutralize each other. So from this, you're just going to get something neutral. So this is going to be a neutral salt, CaCl. Okay, let's do it with calcium fluoride. So here, again, HOH. I'd like you to pause the video and determine what the two salts are that are formed, or I'm sorry, what the two, the acid and the base is, and whether they're strong or weak. So go ahead and pause the video, and just for calcium fluoride. Okay, so here you're going to form calcium hydroxide and HF, hydrofluoric acid. So CaOH2 is a strong base, and hydrofluoric acid, HF, is a weak acid. So here, overall, this whole salt now, this is going to be basic because you have a strong base. It's going to override the weak acid. So this is a basic salt. This is a neutral. I should write salt. Okay, I would like you to pause the video and see if you can predict both of these. Okay, first one, ammonium chloride, HOH. We're forming hydrochloric acid and ammonium hydroxide here. So HCl, or let's keep these colors consistent. So we are forming HCl, which is a strong acid, and ammonium hydroxide. That's a weak base. So overall, you have a strong acid, weak base. This is going to be acidic salt. So what it's going to form are more hydrogen ions, right? Because those are all going to be released as hydrogen ions. And weak base, not very many hydroxides released. So overall, the solution is going to be acidic here. Okay, now ammonium fluoride, this one's interesting. So HOH. Here we're forming our ammonium hydroxide and our hydrofluoric acid. So we have NH4OH. That's a weak base. And HF, which is, as we know, a weak acid. So, how do we tell if this is acidic or basic? Well, which one of these is stronger? You can't tell unless you compare their Kas, or Kb if it's a base. So, the NH4, right here, so the Ka of NH4+, so at the bottom, the Ka of NH4+, which we calculated way up here at the top. So Ka of NH4+ is 5.6 times 10 to the negative 10. So that Ka equals 5.6 times 10 to the negative 10. So we have our Ka for our ammonium here. That's going to be for this part, the ammonium. Now we need the Kb for the negatively charged ion, the fluoride. So the Kb of fluoride. And we figured that out above, and that's 1.4 times 10 to the negative 11. So, which one of these is bigger? Well, Ka is 10 to the negative 10, that's 10 to the negative 11. Of course, Ka is the bigger number. So Ka is larger than Kb. So because Ka is larger than Kb, it's going to contribute more to the acidic character. So this salt is going to be overall acidic because the Ka for acid is larger. So this is going to be an acidic salt. And here, must compare Ka and Kb first. So in this case, it was an acidic salt. It won't always be acidic. Sometimes it will be basic as well. But you have to always compare your Ka and your Kb of the two ions in the salt, because this trick failed us because it just said weak base, weak acid. So we had to go back and actually compare the Kas. Okay. Last example on this page. Consider the following reaction. Is this process reactant or product favored? First thing you have to know is that Bronsted-Lowry acids and bases favor the side with the weaker acid. And that's because weaker acids dissociate less, and they dissociate less because they're lower energy. So they're okay staying together, they dissociate less, they're low energy. So Bronsted-Lowry, which is the definition we've been using of an acid and base, they favor the side with the weaker acid. Because weaker acids dissociate less, or to a lesser extent. Weak acids and bases are lower energy. Okay, so let's take a look at our Kas of our acids here. So the Ka of HF, we can just read that from above. And our Ka here equals 7.2 times 10 to the negative 4, I think it was. 7.2 times 10 to the negative 4. And the Ka of, let's see, which one is our acid on this side? HOCl. That's our acid because this is our conjugate base. And so that Ka equals 3.5 times 10 to the negative 8. So which one of these is weaker? Which one of these is smaller? So this Ka is much smaller, so this one's weaker. So this is the weaker acid, HOCl here. And so since the weaker one's on the product side, the reaction shifts right, favors the products. So since weaker acid is on product side, reaction favors the products. Okay, that is it for lesson 4.3.1 on strengths of acids, or video 4.3.1.